Okay, you have 1 minute. So I'm about to call time. When I do, I want everyone to stop where they are, just to be fair, okay? So 10 seconds. Oh, I'm sorry. Okay, that's time. All right, so let me come around and pick those up. See, a lot of you didn't finish. That's part of what I want to see. So what were the correct answers on that? Extra? Okay. I'll go through the quiz, okay, since a lot of you didn't finish it. I will go through it, but let me first address a question. Extra? Oh, that's yours, or someone's. Okay. Let me first address a question that was posed to me at the beginning of class over a problem out of the homework. Okay. So look, the idea of that quiz is, my expectation is that you could finish those two problems in about 10 minutes, roughly. If it's taking longer than 10 minutes, then you're not where I think you need to be. Doesn't mean that you don't know what you're doing, it just means that you need to become more efficient. All right? So let me address this first, then we go to the quiz. So this question is about a problem from the homework, from the section 1.4, where you're asked to look at these two different limits, and I never talked about an absolute value. And so it's worth us discussing this. All right, so look at this first one. Limit as x approaches 2. So if you plug 2 into the top, you're going to get 0, and if you plug in 2 on the bottom, you're going to get 0 also. So you're getting 0 over 0, right? Which means you have got to do something. So I think the first instinct was to factor out the top, because it was a trinomial. Did you factor this out? Yeah? Okay, let's do that. So if you factor the top out, you should get x, you could write it either way, x plus 3 times x minus 2 over the absolute value of x minus 2. All right? And I think your question was, can you cancel the x minus 2s? Is that kind of what you're asking me? And the answer is no. All right? And that's because they're not the same thing. So I'd like for you to just take a look at something different than this. And I'll do it in a different color because it's a different idea. What if I was saying, hey, look, what is the limit as x approaches 0 of x over the absolute value of x? All right, so let's simplify this. We're not going to make it as complicated looking. So what's happening as x approaches 0? And right now, am I saying which side we're supposed to come in from? No, right? So let me pick a side. Let me come in from the left, all right? Or let's do right, because that one's the right one first. Okay, so if I come in from the right, let's just kind of think about what's happening as I approach 0 from the right-hand side. If I plug a number in here, like way out here, like the number 1, then what would happen if I plug 1 in here for x? 1 over 1, and I get 1, right? What if I plug in 0.5? 0.5 over the absolute value of 0.5 would still be 1, right? If I plug in 1/10, same thing, right? We're going to get 1. Agreed? So this should give us 1 if we're coming in from the right. However, if we come in from the left, what's different? Yeah, so now let's come in this way, all right? So if we plug in -1, -1 over the absolute value of -1 would be -1, right? If we plug in like -0.5, negative 0.5 over the absolute value of -0.5, that ratio is also -1. So even though the values are the same, like the top and bottom, the number's the same, from this side, they're both positive, right? And from this side, the top's negative and the bottom's always positive. I mean, sorry, yeah, top is negative and the bottom is always positive. Make sense? So the limit from this side is 1, but the limit from this side is -1. Does that make sense? So if we were to start this problem and we were to just go limit x goes to 0 of x over the absolute value of x, if we were to just cancel these and say it's 1, right? Like those cancel to be a 1, that'd be wrong because the answer is not 1, it's 1 sometimes, but it's -1 other times. Okay? So back to this one. Which side are we coming in from? We're coming in from the right. Now we know that this is approaching 5, right? That's approaching 5? Yes? Okay. The question is this piece. So let's just again do kind of like a little number line. If we come into 2 from the right hand side, imagine a number like 2.1. If I plug 2.1 in here, 2.1 minus 2 is going to give me 0.1, right? And then 2.1 minus 2 is going to give me 0.1 again. Take the absolute value and we get 0.1. So this is positive and this is positive, which means these are going to reduce to be a what? A 1. You go with me? So this is going to be, this is turning into 5 and these are turning into a 1. And so the answer here should be what? 5, right? 5 times 1? 5. Rejected. So this should be 5. Now compare that to this one. Again, if we go through and we factor out the top, let me just do it now. X plus 3 times x minus 2, then same story. Okay, this is headed to 5. These I've got to figure out. So now I'm approaching 2, but I'm coming in from the left. So a number like, I don't know, 1.9. So what happens there? Be real careful here. If you plug in 1.9 right here, 1.9 take away 2, that's going to give you a little negative number, isn't it? And then when I do 1.9 minus 2 here, it's going to be a little negative number, but then you're going to take the absolute value. So these two numbers will be the same, but they'll be opposite in sign. So you'll get a -1. So this time it turns into a -1. And that one stays a 5. So your answer here should be what? Negative 5. See the difference? Okay. Very good question. I'm actually giving a quiz in my Cal 2 class tomorrow where at the end of the problem the answer is sine x over the absolute value of sine x. And I'm curious if anyone's going to turn that into 1. That would be incorrect, right? That would be incorrect. So this actually does creep its head out a little bit later. All right, now the quiz. So what's going on the first problem with the quiz? What sort of limit do we have? What form are we getting when we actually take that limit? X goes to 0, tangent of 3x over sine of x. So what's happening here? You plug in 0, you get what over what? 0 over 0. And anytime you see that, you've got to do some algebra, some sort of trick, right? So this is the one where you have to peel it apart and kind of make things appear and make it work. So limit x goes to 0. I'm going to rewrite tangent of 3x as sine of 3x over cosine of 3x, right? But I'm actually going to do it, I'm going to rip it apart now because of time constraints. Okay, so there it is, all completely ripped apart, right? So which of these factors is causing the problem? The sine x down here, right? This one's okay, because cosine of 0 is 1. Okay, so we don't get division by 0 here. Here we get 1 over 0. Okay. This one's okay also, because 0 over 1 is defined. 0 over 1 is 0. So this is the one that's causing the problem, so this is the one I need to fix. And the only way I can fix that is to do what? No, what do I need above it? I need an x. Why do I need an x? Because I gave you a rule last class, or a formula that says that anytime you have sine of junk over junk, junk goes to 0, that limit's 1, and you can also flip it over. So if you have junk over sine junk, so you have to know that. I mean, that I told you, burn it in, right? So I have to put an x up here, so I have to multiply over here by x over x, right? And then I'll slide this x right here, and that will take care of that one, right? This will become a 1. This will be 1, that will be 0. So we created a new problem, though, because we have an x on the bottom here. So how do we fix that? 3. Yeah. 3. What's that?
3 over 3.
Okay, but why? What are you going to do?
The x will go to the first one.
Okay, so you can take the x on the bottom and slide it under this one, and then all you're missing is a 3. So now you come in here with your 3 over 3, right? And you're going to slide the 3 under here. So after you do all this, the next line should be limit x goes to 0, sine 3x over 3x times 1 over cosine 3x times x over sine x times what? 3 over 1, or just 3. Okay? So that x left, this 3 left, but that 3 was still there. And now when you actually take the limit, this is going to go to 1. Sine of junk over junk. Is the junk going to 0? Yes. 1 over cosine of 0, that's 1 over 1, that's 1. Junk over sine junk, the junk's going to 0. This is 1, and this is 3. The answer's 3. Okay? That's the first one. Now the second one, yes?
So I just put 3x over 3x. Is that okay?
What do you mean? Oh, just, yeah, you don't have to have those separated.
I know. But
Sure.
okay.
Yeah. Now, did you do 3x over 3x because you wanted a 3x here?
Yeah.
Okay, so
well, I
that's
still had a problem if I'm still going to have that x left.
yes.
So I just kind of.
Okay, so the only reason I'm asking is because when you start this problem out, and when you're at this stage right here, yes, you could say, hey, I could put a 3x here. But the thing is, you don't actually need to fix this. This isn't the thing causing the problem. This is the thing causing the problem. Now, it works out. Yeah. It still works out. But, if you're looking at any limit, you don't want to start working on something that you don't have an issue with, right? You want to start working on the thing that you do have an issue with, which is this. But it works. Okay, the next one, it's same, limit x goes to 0. All I did was, there's only one little change to it, right? Well, we're coming to 0 from the right, from the left. Okay, so that, and then on top, it's not tangent 3x, it's tangent 3x, and then take away 4, and the bottom is still sine x. So, yeah, so when you take the limit here, the form that we're getting is negative 4 over 0. And when we see that, we think to ourselves, fixed over 0, okay? This is fixed over 0. And anytime we see fixed over 0, we need to be thinking that our answer is either going to be infinity, negative infinity, or it could possibly not exist. And the times it doesn't exist is when this is not here, and you have to check from the left and the right. But if you're only coming from one side, we should get either infinity or negative infinity on this. Okay, so now what we need to do is determine, is the top positive or negative? Do we know? It's negative. So we know we have a fixed negative number on top. The only question is are we approaching 0 through positives or negatives here? So we go back to this, we look at the denominator, we say, hey, that's the sine function, right? And we want to be approaching 0 from the left. So if you just graph sine, and then make it go backwards a little bit, here's 0. If we're approaching 0 from the left, that means we're moving on the sine function like that, right? Those little values on the sine function are below the x-axis, which means that they're little negative numbers. And so we know that we are approaching 0 here through negative numbers. And so the ratio there is infinite, positive infinity.
Would it be okay if we still wrote the positive sign near the infinity?
Oh yeah, that's okay.
Thank you.
Mm-hmm. Okay, so if on the second problem you were trying to rip it apart and do junk over junk, right? If that's what you were doing, then you're missing a major part of this, which is you always want to look at what you have first, and then that will dictate which road you go down, right? Fixed over 0, it's just a matter of analyzing the sign of things. If it's 0 over 0, now that's when you get to play with the algebra, okay? All right, so remember, these quizzes are not about, trying to damage your grade or anything. I'm trying to I'd rather you make a mistake on a quiz than on a test. I really would. And it also gives you some idea of what I expect, and it also gives you that practicing with the pressure and the time constraints and all that, That way when the test comes, which is when? It's around the corner. It's coming, but.
Let me ask a question
Okay.
really quick.
Yes.
If I keep writing fixed a certain amount of times, will I be able to remember it?
Will you?
I screwed up and I panicked and I wrote
If
something else
you-
instead of fixed, but I wrote the right sign here where the word fixed should be.
You don't have to tell me. You don't have to say fixed. Like, you don't have to. I'm not quite sure I understand your question.
Well, just the word fixed. Like, does it just have to be that word, or could you just write F?
Yeah, right. Whatever.
Well, I wrote something completely.
Yeah.
I wrote something completely.
I just don't want you trying to do a problem that has a fixed number over 0 and try and do algebra.
Okay.
That's what I don't want to see.
So you just want the answer. You're not going to worry too much whether the word fixed is there or not.
That's right.
Okay.
I don't need the word fixed. But I need to see that you're doing something. So on a problem like that, I do expect to see some sort of work. If you just say, oh, I'm going to flip the coin, it's either infinity or negative infinity, that's not going to work. Okay. All right. We move on. So last class we were talking about fixed over 0, right? And how we get these different scenarios that pop up. So basically from last class, we were taking a limit where we had something going to something, right? And in here we had some stuff, whatever it was, and what we were getting was fixed over 0. And we kind of now understand that we have a way of dealing with this. And anytime we have this, we have asymptotes. We have vertical asymptotes in our graph of our function. So now we switch gear. Oh, well, I wanted to say that our answers here would be either infinite or negative infinity, or does not exist, right? So those were the possible answers that we could have got. So now, today, what we're going to do is, instead of getting an answer of infinity or negative infinity, okay, we're going to take limits where this thing here goes to infinity. And then what we're going to do is we're going to see what we get. So the idea here is this. Whenever we've done this limit before and we've said like x goes to 2, right? That means you'd have to imagine coming into 2 on the function from both sides, right? But now we're not going to let x go to 2, we're going to let x go where? To infinity. Now where is that? Where's infinity? It's, you have your y-axis, your x-axis. Infinity is way out that way, right? So what we're really asking ourselves is, what is this function doing? What is this function doing way out to the right? Okay? Does that make sense? So this is really just asking us to find the end behavior. Now in this particular, oh, it's okay. I thought we had a cat in here. Was that a cat? Is that what I heard? Yeah. Okay. Sorry, this is finding the right end behavior, right? Because as you go to infinity, you go out that way, that's to the right. So this is basically saying, tell me what the function is doing out that way. And then what if I want to figure out what it's doing that way? I'd change that to negative infinity. So I could do the limit, whatever goes to negative infinity of the function, and this will give me my left end behavior. So do you see the major difference between these two limits? This one, your limit, you're heading to a number, And what you're getting is like fixed over 0, but you're still heading to some number on the number line. And you're asking what the function does as you get close to that, and you get like asymptotes like this. This one is saying, okay, look, follow the function out that way. Is it doing this, or is it flattening out to something? And then this one is saying, look out that way. Is the function going up? Is it down? Is it flattening out? So these, in college algebra, these were called horizontal asymptotes, weren't they? Horizontal asymptotes, what your function does at the two ends? Okay. So that's what we're going to be working on now. So the language for this is these are called limits at infinity. Okay? So what we did before last class were called infinite limits. That means we were getting an infinite answer. Our limit was infinite. Here we're doing limits at infinity, meaning we are headed to infinity, all right? Either left or right. So those are two different types of limits. All right, so let's see. Yeah, we're going to take a couple of examples. Let me make this not so big. Boom. Okay, so here we're gonna start this with the graph. Okay, that way we can at least feel comfortable with this. If we take the function f of x equals 1 over x, and we ask ourselves, you know, what's the right end behavior of this, and what's the left end behavior of this? Then, if we want to know the right end, what do we do? In a calculus class, what do we do? Take the limit as x goes to infinity of the function, right? What do we do if we want the left end behavior? At this time we take the limit and we're going to let x approach negative infinity of the function. And you can tell by the picture, I think, what's happening. What happens to this function as we head out to the right? Danielle? Oh, she's not here. Okay. James? Where's James? Sorry, I lost your stick here. Hold on, I lost your stick. Okay, well, if you come up again, Where are you? So as we go out to the right, as we take the limit as x goes to infinity, what is that function doing visually?
Getting closer and closer to the horizontal
0, right? The y value is headed to 0. So do we all agree that this is headed to 0? Okay, now I want you to think about it algebraically. You have the number 1 on top, right? And then this number is what? As x gets big, this number is getting big, right? So what happens to a fraction if the numerator is fixed and the denominator becomes infinite? Infinitely big. It should get really small, right? And so where does it approach? It approaches a really small number. And what's a really small number? 0, right? Hold on just a second. Okay. Make sense? All right, now what if we go out this way? Visually, it's headed to 0 again, right? But this time it's coming in from the bottom. And the reason it's coming from the bottom is because as we plug numbers in here, as we go to negative infinity, we're plugging in negative numbers, right? They're getting bigger, which means this ratio gets smaller and heads towards 0 also, right? Okay, so on your little sheet, where you got that little cheat sheet with the boxes on it that you're not allowed to use on tests, but you have to somehow memorize, right? This thing, right? Do we have this on here? Yes. Where are we looking? Bottom right. What does it say? Fixed over infinity, right? And notice it says fixed plus or minus. That means it doesn't matter, okay? So I'm telling you that if you ever have a fixed number on top, doesn't matter if it's plus or minus, and the bottom is going to infinity or negative, I didn't put it here, it doesn't even matter which infinity this is headed to, okay? As long as the top's not moving and the bottom is getting huge, we should get 0 as an answer. So out of all the limits we've done, this is probably the easiest one to do because there's not a lot of work to do, right? Like in the previous one, when we have fixed over 0, we have to check and see if it's positive, negative, negative, positive. You know, Here is fixed over infinity, boom, we're done, 0, all right? But there's a little asterisk, all right? Look on the bottom of this thing. What did I say on the bottom here, this in words? I typed one little sentence here. What did I say? Here, when I say fixed, what I mean is, so this number right here can be any non-zero number, like 1 or 5 or negative 10, or what? And or what? Bounded. What do I mean by bounded? So let me give you an example of what I mean by bounded. What is the limit as x approaches infinity of cosine x over x? You know what? Let's not do cosine. Let's do sine. And the reason I did sine is because somebody in here has these neurons firing in their brain right now and they want to say the answer is 1. No? Why is it not 1? Do we have junk over junk? I mean, do we have sine of junk over junk? Yes. Is junk going to 0? No. Okay, so this is not 1. However, does it fall into our table here? Do we have fixed over infinity? Well, we have infinity, right? On the bottom, it's headed to infinity. Do we have fixed on top? What does the sine function do as you head out to infinity? Imagine what the sine function looks like as you head out to infinity, right? Just up and down, right? Up and down. Is that fixed? No, but what did I say here fixed really means? A number or bounded. Is this function bounded?
Yes.
What is it bounded between?
It's bounded between sine x and...
What are the values of sine bounded between? 1 and negative 1. So this is a bounded function, right? So I have here bounded over infinity. And according to what I'm saying, the answer here then should be what? It should be 0. Okay, but let's think about why it's 0. And I think it might be worth it for us to just look at the graph. What is happening to the denominator as if I were to graph this, sine x over x, what's happening to the denominator? Denominator is getting bigger, right? Numerator keeps oscillating between negative 1 and 1 though, right? Like the biggest it could ever be is 1 and the smallest it could ever be is negative 1. And so even though it's fluctuating, the denominator just keeps getting bigger and bigger and bigger and bigger. So that ratio should start to drop away. So here it comes. There it is. Let me get this out of here. And let me kind of zoom this out. So remember, we're headed to infinity. So take a look at that graph. I really need to change my range here. See if I can do this easily. I don't remember if this is the way you do it or not. Yeah. Go away. You see that? So initially, we have the sine. It's trying to go up and down, but you keep dividing it by a number, right? And that number keeps getting bigger and bigger. So it's going to start to squeeze it down. A really cool way of seeing this is thinking back to pre-cal. Do you remember that from pre-cal? What's the number in front of sine x? The amplitude, right? Okay, so you see that sine x over x? Could you rewrite that as 1 over x times sine x? You could, right? And if you look at it this way, then my amplitude is actually like changing, isn't it? So I have something in front of sine. This is changing the amplitude as you move out to the right. And as x gets big, this gets small. So what I'm doing is I'm smashing my amplitude down as I try and draw the sine function. That makes sense? So you get this. And as I go out to the right, even though it's oscillating, what's happening? The amplitude keeps shrinking, doesn't it? Now, as I move through here, I'm crossing through the x-axis, aren't I? I'm going a little bit below and then back up, but every time I do that, it's just a little bit closer and closer, right? So the limit is still 0. Even though it keeps going above it and below it, the limit is still 0. Because the further I move out, the smaller, the more narrow that little strip gets. Does that make sense? Okay. Why are these useful functions? Let me show you another one. This one right here. Sine x over e to the x. Now we haven't talked about e to the x much, but what would happen if I take the limit of this as x goes to infinity of sine x over e to the x? So we already know on the top it's bounded, right? It's just going to keep oscillating. But on the bottom, e to the infinity, that just means look at the e function. What is the e function doing as you move out to the right? So we remember what that looks like. It was one of our first days in this class. We talked about exponential functions look like that, right? So if I look at this e to the x and I say, hey, go out to the right, that thing is doing what? Taken off to infinity, right? So we have bounded over infinity again. And this should go to 0, all right? But you can look at it exactly the same way we did the previous one. It's like 1 over e to the x times sine x. So that amplitude is now a function, right? Now which one do you think gets smaller faster? 1 over e to the x or 1 over x, the one we did before? Which one do you think shrinks faster? 1 over x, so I'm asking you to compare, versus 1 over x sine x. Which one of these two guys gets smaller faster? As x gets big, 1 over e to the x, because e to the x grows very fast. So 1 over that should go small very quickly. So I'm going to graph that one, and we'll compare them. Then I'm going to talk to you quickly about why this is such an important type of function to understand. Sine, x over, I don't know, e, let me just try it. E raised to the x? You can probably do that. All right. Okay, I need to move this back over here so we can compare them back here. Wow. Okay. So the blue one is the sine x over e to the x. And right here is 0, so it starts trying to be a sine function, right? But right away, that amplitude starts getting smashed down. And look, it almost goes like flatline, doesn't it? But if we zoom into that, you'll see it's not flatlined. Boy, it looks flatlined, doesn't it? Oh no, get away. Wow. Come on. Okay, it looks like a flat line, but I promise you it's not. Let me zoom out. Move over. And zoom in. Boy, it happens so fast, doesn't it? Look at how quickly, I mean, just right away, just smash that thing down. Yeah? Yeah. Okay, so why would these be important functions? Let's say I take a ball, right? Take a ball and I just drop it, like a basketball. What's going to happen? It's going to go down, hit the ground, come up, hit the ground, come up, hit the ground, come up, right? So you could say, yeah, it's kind of like a sine function. Like if this is time, I start the ball up here, and as time goes, the ball drops, right? Hits the ground, comes back up, hits the ground. It does some sort of oscillating motion, right? Like this. But we all know what happens to the ball. Like you don't drop it, walk away, go do something, come back, and it's still boom, 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 right? Like it doesn't maintain the amplitude the whole way, right? The amplitude starts to diminish, and eventually, doom, 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 to nothing, right? And so you need a function that would actually behave like that. And these types of things behave that way. It still acts like a bouncing ball, but as time goes on, eventually it's kind of like 0. Make sense? Okay. So the big takeaway is that bounded over infinity always goes to 0. Or fixed over infinity always goes to 0. Give me a second here. So let's try this. Limit as x goes to infinity of x squared plus x plus 1 over 4x squared minus x plus 2. Now, before we can actually dive too deep into this, we need to all understand something very important. So let's take a look at the numerator, and let's see who's going to go here. It's going to be, let's see, there's two oh, no, this is Danielle? Daniela? No. Bateman. What is it, Danielle? It's Danielle, okay. So Danielle, yeah, I said Danielle wasn't here, but that's a different one, sorry. Okay. So on this, if x goes to infinity, right? X goes to infinity, what does x squared head towards? Infinity plus infinity. What's infinity plus infinity? Infinity, okay, plus 1. What's infinity plus 1? Still infinity, all right? So the numerator is becoming infinite. The whole idea is that it's just blowing up, right? So the numerator is headed to infinity. Where's the denominator headed? So I'm going to stick with you, Danielle. 4x squared is headed to where? Infinity, right? Because it's like infinity squared, which is infinity, times 4, which is still infinity, right? Now, then we're doing what? Subtracting from it what, Danielle? Infinity. So what's infinity minus infinity? Is it 0? So that's, yeah, so infinity plus infinity I think most people have no problem with, right? Huge number, add another huge number, you got a huge number. But what does infinity minus infinity mean? It's not 0. Not always, sometimes it does turn out to be 0, but you have to think about what we're saying. We have something getting huge, right? Minus something getting huge. This is not, we don't know actually what's happening here. Okay, we don't. But I'm going to do it on the side. So Danielle, you're going to help me out here. I'm curious, Danielle, just to see what happens with that, because the plus 2 really isn't going to change anything, right? Just plus 2, who cares? So this right here, you said that's headed to infinity, that's headed to infinity. What's infinity minus infinity? And we said we don't know, okay? So Danielle, go back to college algebra. In college algebra, if that wasn't there, like what would be something you can do with that expression? Factor out an x. Okay, so let's factor out an x. If we factor out an x, then you'd be left with 4x minus 1, right? And now look at that. That's multiplication. Danielle, x is headed to infinity, right? So this is headed to infinity. Times, now what is this headed to? Infinity minus 1, which is still infinity, right? But now you have this, infinity times infinity, which means, what's infinity times infinity? So a huge number times another huge number should give you a huge number, right? So this is infinite. Do you understand that? So in this particular case, even though this is headed to infinity, and we're taking away something that's headed to infinity, what this answer is telling us is that this term dominates this term, okay? The 4x squared grows so much faster than this one. Well, it should. It's quadratic, that's linear, right? So this quadratic term dominates this one, and that's why that's infinity. Yes? So let's come back over here, Danielle. Now, from now on, when we look at this, we're going to be considering the powers. We're going to be saying to ourselves, okay, look, if I have a higher power, that term's going to dominate anything lower than it. So this right here was headed to infinity, right? Minus infinity, but because that's linear, this one wins, okay? So infinity, who cares? And then plus 2, who cares? So the bottom's going to infinity. Y'all on board? Okay, so what do we do when we have infinity over infinity? We have not had this yet. But it's on your table, it's on your chart here. back up to the top left corner, this is basically like 0 over 0. This is like getting 0 over 0. We have to do some algebra. Now the reason it is because remember, infinity is not a number, right? Infinity is not a number. It's an idea. All we're saying here is that the numerator is growing without bound, and the denominator is growing without bound, and we want to see if there's some ratio here. Are we getting some answer? Now, do y'all recognize this problem at all, like from college algebra? Like this is a rational function right there. And what we're really asking for is the horizontal asymptotes, right? Because that means what's happening is we go out that way, or if we change that to negative infinity, out that way, right? Do you remember how you found the horizontal asymptotes of a rational function in college algebra? It depends on you who taught you, I think is what it's going to come down to.
Just have the x go to like divide all the x by the degree, and then they
There you go. Okay, so that's one way, and that's the way we're going to do it. There's another way. So what's being suggested here is that what you can do is you can divide every single term by the highest power of x that you see in the denominator. That's one method. The other method was this thing where you compare the degrees. And if the degrees are the same, then it's the coefficient of this one over the coefficient of that one. That's another way. Okay, we're not going to do that one. We're going to do the calculus way, which is to do algebra. Okay, so, and you'll see why. You'll see why in a second, because I'll give you one that you can't do if you learned the other way in algebra. So we're going to go here. We realize we have infinity over infinity. We need some algebra. And so the algebra that we're going to do is we're going to say, look at the denominator, look at the highest power of x you see, which is, sorry, I need to leave a little room up front. The highest power of x we see is x squared, right? So what we're going to do is we're going to divide every single term by x squared. Yes? But I'm actually not going to write that. What I'm going to do is I'm going to do what that is algebraically. Dividing by x squared on everything means multiplying by 1 over x squared here and 1 over x squared here. That's 1, right? So if I do this, I can pass this through and do that and pass it through. And it has the same effect as dividing everything by x squared. But you'll see in the next example why this is important, all right? So let's do this. Any questions at this point? Maybe you have a question as to why we're doing this. Work it out first. Let's work it out first, then you'll see why we did come through and divide everything by the highest power of x. So let's pass it through. Limit, I have not taken the limit. X is headed to infinity. And Marcus? Where's Marcus? Okay, Marcus. Doing all right today? Yeah? Okay. I would like to know what we get if we pass this 1 over x squared through. So divide each of those by x squared, and what would we get on top? X squared over x squared, which is 1, okay, plus 1 over x, and finally 1 over x squared, right? Okay, and then go ahead and do the bottom since you seem to have this, no problem. 4 minus 1 over x 2 over x squared. Now Marcus, now that you see this, do you see why we did this? Yes? Can you help explain?
Because now there's a common denominator.
Okay, so what were we talking about right before this? When I was showing you the graph of the sine, the whole idea was if we had fixed over infinity, right, that went to where? 0, right? Do you see what we've created here? A bunch of fixed over infinities. Okay, that's what we've created. And the way, if we go back and look at the original problem, if I say, look at the highest power here and divide by it, then I know I'm going to get at least one term that's a number, right? 4. And then everything else, because these are lower powers, should be some sort of fixed over infinity. Yes? Now, why only worry about the denominator, not the numerator? Because what you have to guarantee me is that you leave at least one constant in the denominator. Because if you're looking at the numerator, you can go mess with the numerator and wind up wiping everything out on the bottom. What if you wiped everything out here? Like this is going to go to 0, that's going to go to 0. What if that went to 0? Then you have 0 on the bottom, and then you're back where you started, kind of, because you don't know what happens, right? So the whole idea here was to pick the highest power that we see in the denominator, divide through by it so that we're left with one constant, and then everything else goes to 0, and then we're just going to have to see what happens upstairs, okay? We'll just see. So now we take the limit. So no more limit now. And Herman? All right, so tell me what you got. As x goes to infinity, we get here? There's no x. 1, right? So 1 plus, where's that headed? On the bottom. So 1 over infinity is headed to where? No. Fixed over infinity. No? We just talked about it. No? 0. Okay? Burn it in. All right? Fixed over infinity goes to 0. So that goes to 0. Next one, Herman, goes to 0. Fixed over infinity, right? Are you following that? Okay. On the bottom, 4, there's no x, right? So that just stays 4. Minus 0 plus. So we got fixed over infinity again, right? And so what's the answer? 1/4. Right? That's a lot of work just to get to that. And I realize in algebra there's shorter ways. The shortcut in algebra is this. If these have the same power, right? You look at this coefficient and that coefficient, and you just do 1/4 and that's your answer. But do you see why it will always be that way in college algebra? Because if these two powers are the same, then when you divide through by that power, these two numbers will always be left. Everything else will go away. Now, what happens in college algebra when that's smaller than that? There was another case. There was like 3 cases you had to look at. Exactly, okay? So even though those are nice little shortcuts, they only work for rational functions. So let me show you an example where you have to throw that out the window and you can't use it, all right? And that will maybe convince you that this is more, I guess, useful. Let's try this. Yes?
I have a question.
Uh-huh.
So what if it's like x squared over x to the third? How would you go about multiplying that by that 1?
Going to infinity?
Yeah.
Okay, so like if I had x squared over x cubed, just like that? You don't want me to do anything else?
I mean, like, if it was, like, say that same problem we had, like the x squared plus x plus 1
Uh-huh.
over 4x cubed minus x plus 2.
Okay, well, let's do it. What was, give me the problem again. It was x squared,
plus x plus 1
okay?
divided by 4x cubed minus x plus 2.
Okay, so let's change it to that, right? So same thing here. You first check to see what's happening. Okay, so top is headed to infinity, right? And then Danielle and I went over there and we talked about this. These right here is going to head to infinity because this dominates this one, right? So the subtraction doesn't matter. So the bottom heads to infinity, so we have infinity over infinity. So that means we need to do some sort of algebra. And in this case, we look at the denominator, highest power of x, we divide through by it. So I'm going to go 1 over x cubed here, over 1 over x cubed here, multiply that through the top. And Jackson, why don't you just tell me what we would get for this as we multiply through? So on the top we get what? 1 over x. 1 over x squared. And where are all those going to go when you take that limit? They're all going to go to 0, okay? And that is not a problem, okay? Because the bottom is going to be what here?
The bottom is going to be
4
minus x,
1 over x squared plus 2 over x cubed. So do you see how valuable it is now that that thing didn't go to 0? Because the top is going to go to 0 when we take the limit. 0, 0, 0. The bottom is always going to have a number that's not 0. And so our answer is going to be 0 over 4, which is just 0. And back in college algebra, if you want to go to those little shortcuts, we said if it's, I heard you say top heavy or bottom heavy or something. If we have the power down here bigger than this, then they said the horizontal asymptote was the x-axis, y equals 0. And that's because you're always going to get 0 out here. You're always going to get that answer. If the numerator is degree is smaller than the denominators. I always have trouble saying. All right. That answer your question?
Yes.
Okay. All right, so now let's try this one. How about x, 3x plus 1 over the square root of 4x squared plus 9. Jasmine? She's not here. David? Garza? David, all right. So you're going to help me, David, just figure out what's going on here in terms of the numerator and denominator, right? So where's the numerator headed? Infinity. And then the denominator.
I would say infinity.
You'd say infinity? Yeah, so this is headed to infinity, right? Plus 9, still infinitely big. And then what's the square root of infinity? Well, it's still big, right? I mean, if infinity is like this huge idea, taking the square root of it's still going to be huge, right? So we still have infinity here. All right, so we need some algebra. Now, this is not a rational function anymore, right? It's not a polynomial divided by a polynomial. It's a polynomial divided by a square root function, and that doesn't have a name. We don't have names for things like this. It's just a calculus function. So, but we're gonna play the same game, all right? We're gonna see if there's a way that we can make everything kind of go to 0, except leaving a constant in the bottom. So we still look at this and we see the highest power of x here, right? Which is squared. So that means we need to divide through by x squared, right? But what's wrong with that? What's the problem with that, dividing through by x squared? It's under a radical, right? I need an x squared underneath that, agreed? So how am I going to make that happen? So let's take a little side note here. If I write down this, everyone, the square root of x cubed, I think everybody in this class is comfortable with this idea, that that's equal to that, right? So what we're doing here is we're saying, okay, this is really the square root of x squared times x, right? And then we're saying that's really just the square root of x squared times the square root of x, right? And then that right there is x, and then that's the square root. So really, for every pair of 2, right, an x can come out. We're all good with that? Okay, so what you've never really thought about, and the way that I like to look at it as a student, when I was a student of this subject, I'm always going to be a student of this subject, but the way I see it is this. If you have a squared in here, it comes out as an x, right? But what if you have an x out here and you want to put it back in? What happens to the x if you take an x and you multiply and you push it into a root? What has to happen to it? It has to get squared on its way in. Okay? Does that make sense? So what I would like to do is come to this limit. I'd like to multiply by something. 1 over something over 1 over something. And what I really would like to have is that whatever I come in here with and multiply, when it gets in there, right? When it gets inside of here, it needs to kill off the x squared, right? Which means that it needs to start out as a what out here? An x, 1 over x. So if I push this in, what happens when it gets pushed in? It becomes what? 1 over x squared. See that? And whatever I do on the bottom, I have to do on the top. So I'm not going to be multiplying by 1 over x squared by 1 over x squared. I'm not doing that. I'm doing 1 over x over 1 over x. So now let's multiply this in. It gets pushed in, and then this one just goes through. So limit x goes to infinity. And what's up top? 3 plus 1 over x. Okay, on the bottom, I'm going to take my time with this. I have the square root. The 1 over x got pushed in, right? So when it got pushed in, it became a 1 over x squared. Right? We square the top and bottom of it. Goes in the root. There it is. But that still has to be distributed through to the 4x plus 9. And now I can distribute it, right? Here and here. So limit x goes to infinity, 3 plus 1 over x over the square root. Okay, what is it? 4, because the x squareds cancel when you do that one. And then plus 9 over x squared. And at this point, I think we're good. Because now if we let x go to infinity, things start going away, right? This stays, plus that goes to 0. Square root of 4 stays, plus that goes to 0. So when I apply the limit, I let x head out to infinity, I should get 3 over what? Square root of 4, which is just 2, 3 halves. This thing's headed to 3 halves. As you head out to the right, this thing is going to horizontal asymptote down to 3 halves. All right. So I've had this thing on my mind, and I keep forgetting to tell you all about it. It's a part of our mathematical language that can be confusing, so I just want to make sure we're all on the same page with this. This is not really related to this, but important nonetheless. Okay, if I give you two numbers, let's say I give you the number 2 and I give you the number 7. Which one of those is smaller? This is not a trick question. 2 is smaller than 7, right? Okay. What if I give you the number -1 and 1/2? Which number is smaller? Okay, so -1, why -1? Because it's further left on the number line? Or half because it's what? Closer to 0? So there's some gray area here. And that's why I'm bringing this up. When we say small, what do we mean? Right? What do we mean? So one way you could say small is close to 0, right? Like if you take a number that's really close to 0, like 0.0001, that's a small number, right? That's a very small number. -2 is also smaller than it. Do you see what I'm saying? Like small to the left or small close to 0. And so we just have to be careful with our language that when we use that word, we know what context we're using it in, right? So is negative infinity a very small number? See what I'm saying or no? Do you see what I'm saying or no?
Yeah.
I look at negative infinity as being a very large negative number. Does that make sense? Negative infinity to me has always been a very, very, very large negative number. I don't look at negative infinity as being like the smallest number possible. I look at 0 as being like the smallest number possible. It's nothing. You know what I'm saying? Okay, so let's just be aware of that language and that the whole idea of small is kind of ambiguous in our mathematical setting. So when I say this is getting small, right? It's heading to 0. It's getting very small. I mean small by heading to 0, not small as in negative infinity small. That's weird. Yeah. All right, so things doing okay here so far? How about limit as x goes to infinity of just sine x? Okay, I'm going to go for this one.